Brilliant. Well, welcome everyone to our sixth TIA Centre seminar of the academic year and the first one back since the Christmas break. And today we're delighted to be joined in person by Professor Azra Raza. I'm sure a lot of you heard a fantastic session yesterday on poetry. And today we're going to talk about the actual science. So I will pass over to Nasir, that's going to give an introduction, and then we'll have a talk by Azra.
Brilliant. Thanks very much, Adam. I am personally delighted and honored to welcome Professor Azra Raza for coming here and in person and talking to us about her research. We had a lovely evening, like Adam said, last night for poetry for healing and some pearls of wisdom that were shared with us that we're really grateful for, and we're looking forward to the talk today. Just for everyone online, we have quite a few people online joining us via Zoom. Good morning, good afternoon, good evening to you, wherever you are. We have some people from Japan joining us as well. Professor Azra Raza is the Chen Soon Xiong Professor of Medicine and co-director of the Edward P. Evans Foundation MDS Center at Columbia University. She's a practicing oncologist, seeing 30 to 40 cancer patients weekly. She also directs Cancer Research Lab. Professor Raza has collected more than 60,000, samples from thousands of her patients. She has delivered lectures on science, medicine, poetry, and literature, and serves as an editor on the website 3 Quarts Daily, posting daily for the last 16 years. I don't know how she keeps up with that. Professor Raza met with President Biden to plan the cancer moonshot, and with President Bill Clinton for 3-day breakthroughs in science and technology retreat. She's also the author of a best-selling book, The First Cell, and the human cost of pursuing cancer to the last. And I'm sure we're going to be hearing more about that in this talk. She and her daughter, Shehzad, they live in Manhattan. And now it's our good fortune that they're both visiting the UK, although we didn't meet with Shehzad, maybe another time. But we look forward to Professor Raza sharing some more pearls of wisdom on cancer research with us. So Professor Raza, the floor is yours.
Is there a pointer or just use this? Do you see it? No. I mean, I have the pointer here, but I'm not seeing it. Okay. Good. Well, thank you, Fayaz. Thank you, Nasir. Thank you, Adam. I'm delighted to be here and present in person some of the stuff we talked about last couple of years ago. So I thought I'd begin by showing you something from this last year, 20, sorry, it's 2 years ago now. 2023 in the United States, we performed 1,423 phase 1 cancer-related clinical trials. Practically 87% of them failed entirely, which means they did not go beyond to stage 2. If you take the overall stage 1, 2, and 3 phase trials, then 95% trials in cancer fail completely. And what is the cost of this failure? 50 to 60 billion dollars are thrown down the drain. Just to show you a comparison of what this number means, I come originally from Pakistan, a country of over 250 million people, and the entire budget for the whole country is $34 billion. And in just phase 1 failed clinical trials, we are throwing away $60 billion. In addition, half the patients practically, by the second year of their diagnosis of cancer, are financially completely ruined. Not only just the patients, their next generations are affected, which is completely unacceptable. Now, of course, disease requires, as you know, brutal therapies with unbearable side effects, and timely intervention and progressive abnormalities morph into disease. This solution that we are looking for cannot be incremental. It has to be now a radically different solution. And this is why I wrote the book, The First Cell, because I decided to look at everything related to cancer through the prism of human anguish. What is it we are actually doing to the patient? And I wanted to begin by showing you the solution, because one of the criticisms of my approach has been, well, you have diagnosed the problem accurately. Where's your solution? What are you suggesting that we should? So I thought I'll just begin by showing you the solution. And that solution has been actually created by two absolutely brilliant biomedical engineers at Columbia University, Professor Ken Shepard and Professor Sam Sia. And this is the solution. Now, the solution is not in the syringe. This solution that I'm talking about is actually in the needle. And in fact, Sam and Ken actually gave me this thing to show you. This literally is the solution that I'm holding in my hand, in the needle. And what is in the needle is, I'll show you in the next slide here, is that I've laid this out. This has sort of been laid out here on a thin film. This film, this thin film is rolled up and is inside the needle. And what does the film contain? Two electrodes, two transducers, and a tiny built-in chip. That's a little computer. So what happens is that this is all very technical from Sam and Ken, but I'll just tell you what happens in English. Basically, the two electrodes will create an electric field. So this film is inside the needle. We insert the needle into a major blood vessel, and the film is implanted inside the blood vessel, unfurls, and resides there forever. And now what happens inside the blood vessel is it will create an electrical field. So every cell that passes through causes impedance of the electricity. And that impedance, if the cell is small, the impedance creates a small signal. If the cell is large, it creates a large signal. And those get recorded. Those get recorded on this film. On the chip here. Now, the point I'm making here is that this has already been successfully tested in rabbits and pig models. So large mammals have been tested. Now, I felt, by the way, that in order to make any real change in science, you need consensus, because I've been a lonely voice in this field of early detection, revolutionizing early detection, rather than trying to kill the last cell, try to get focus on the first cell, find cancer early and nip it in the bud. I've been saying all this since 1984. People listen to me, they agree with me, they say this is fine, we know it already, that early detection is good, and then they go home and continue their work on the last cell. So I decided that it may be a good idea to try and build consensus. And I called my colleagues in various universities, created something called the Oncology Think Tank. MD Anderson, Harvard, University of Chicago. I mean, these are some of the top institutions in our country. And we got together, we held 17 2-hour long meetings. We had industry participants, everybody who was working in early detection. And after these long meetings, we wrote an opinion paper that got published in Scientific American. And this first author, I'm the first author, but there are 30 co-authors with me. And basically, everyone agreed with me that in order to really cure cancer in a patient-centric, compassionate manner, without using brutal therapies, we have to find it much earlier than stage one. In fact, at the first cell stage, which is a very different stage than stage one cancer. So the conclusions of the think tank was that the best solution is to detect that wellness to disease transition at the first cell stage of cancer. And the strategy is, the ideal, of course, would be to monitor every healthy individual and start looking for the first cell when it appears. But some people will never get cancer, others may not get for 30 years. So the second best solution would be to start with a smaller group and identify individuals who are at high risk of developing cancer and start monitoring them, waiting for the first cell to appear. Is there such a group? Yes, there are multiple such groups. But the one group that I have been following since 1984 is something I'd like to show you now. I started my career by studying and treating patients with acute myeloid leukemia. Within a few years, it was very clear to me that in my lifetime, this disease will not be cured. It is one of the deadliest cancers known to mankind. So I started thinking, well, what is the only good news you can give a cancer patient? It is that we found it early and we can cure you. So how do you find acute myeloid leukemia early? Because by the time you diagnose, there are billions of cells circulating all over. And that's when it occurred to me that we should look at people who are at high risk of getting AML. Are there such people? Yes. Those were called pre-leukemia. These are patients who will just present with a low blood count, like anemia or low white count, or all counts are low. And they come to their doctor, and a third of these individuals can develop acute myeloid leukemia. So I said, wow, this is the one group I should start studying and following. And the idea was that we can prevent the appearance of acute myeloid by intercepting early in these individuals. And it's interesting, in 1984, when I made up my mind about this, by the way, I don't feel particularly disturbed by this, because whenever I'm doing a Zoom from home, especially if I'm on an international podcast, a jackhammer starts going off above, and there is panic to call the super in the building and start yelling at him, and he'll say, no, we have to do it for 10 minutes, and everyone has to wait. So don't feel badly. I'm used to this kind of interruption. Being from New York City, we can survive this. So when I realized this whole trajectory about studying patients with pre-leukemia, the second thought that occurred to me was, well, I need samples to study. Now, if I had gone to school in the West, my next move would have been to make a mouse model. But I was a stupid immigrant and very naive. I didn't even know that such a thing was possible. So I just said to myself, I need samples to study. I should start saving samples on my patients. But the other thing that helped, and I want especially the young people to realize this, because I had landed in America in January, fresh out of medical school, and my residency was not going to start until July. So I had 6 months. And I panicked, thinking, my God, somebody will cure cancer in 6 months. I'm going to be left behind. So I showed up at the cancer center and said, I want to start working today, literally within a couple of weeks of landing. And they had a spot in pediatric oncology where I started a fellowship. But within 3 months, they threw me out. Not because I'm stupid, but because I was crying the whole time. I could not handle children with cancer. You have to sit in them, and those days were brutal days, especially You have to do lumbar punctures and Maya reservoir insertions and bone marrow biopsies. It's horrible to do it to little 2-year-olds and stuff. So they got so fed up of me, they said, look, you belong in the adult oncology and threw me. The first thing I realized when I started working in adult oncology is that the same combination of 4 drugs that can cure acute lymphoid leukemia in children had 0.00 effect in adults. And I realized that, of course, it makes total sense. In a 2-year-old, the normal cells are practically virgin cells, newborn, they're still developing. Whereas in a 70-year-old with the same cancer, the rest of the cells, including the leukemia cell, have received 1,000 cuts already. And so the way they metabolize a drug is very different than the way a naive cell is going to metabolize a drug. And so it dawned on me immediately that even a littler version of ourselves cannot serve as a model for the adult. That's when I started reading about models. And the person that impressed me the most is the father of cybernetics, Norbert Wiener. In 1946, he pointed this out very clearly. The best model for a cat is another cat, preferably the same one. In other words, even Nasir cannot serve as a model for me because his lifestyle is different, his family history is different, his past medical history is different. So how can he and I respond the same way to a given drug? In other words, you have to study the individual and only make decisions based on their protoplasm. And so these were some of the things that for me seemed very obvious and very logical. But you don't even think like that if you are raised in a certain indoctrinated, dogmatic world where you just have to go through these steps of doing your MD, then PhD, then making a mouse model, and then you get siloed into this and you don't even have time to think about alternative. And so I started saving samples on my patients, and today I have the largest tissue repository in the world. I have saved over 60,000 samples, and the beauty is that they've been longitudinally obtained as patients traverse natural history of their diseases from pre-leukemia to leukemia or to death. Nobody in the world has these samples except, and there are no grants or that you could apply for because no one does this, or especially in 80s, no one was doing it, and 90s. You know who supported me throughout? My patients. They would want to give me money, and I'd say, no, give it to my tissue repository. I mean, right now it costs me $2.2 million a year just to maintain this tissue repository. And I raise funds literally by holding fundraisers, by having my benefactors and my donors give me money to support this. Because there is just no respect for something like that. Everybody and their grandmother is busy studying animals. Now people in the last 10 years or so have started saving samples, but they don't have the perspective of the disease that I have because this goes back 35 plus years. And so the reason I'm taking a little while to talk about this tissue repository to all of you is because I can't imagine a group who should be more interested in this kind of progression of a certain disease. How does it go from the first cell to becoming this malevolent end stage monstrosity that just kills, that we have no control over at all? Now, Nasir and Fayaz and I have been talking for several years about this, and Adam, of course, that we could consider doing something like this. Let's say when the patient has pre-leukemia or MDS, we have their samples. Then we have their samples when they developed acute leukemia. Some people develop leukemia within 3 years. We call them short survivals, but some can live very long, like 10 years before they develop leukemia. Those we call long survivors. So, can we at diagnosis, if a patient is sitting in front of me in my office and I give them a diagnosis of pre-leukemia, they'll ask me, Dr. Raza, you're telling me I have MDS. What does that even mean? Should I be completing my bucket list? Am I going to die within a year? Or should I be planning for my grandson's graduation in 4 years? We have no way of telling that. The best scoring systems we have is like flipping a coin. It's correct 50% of the time. Because what it's telling you is that if we had 100 patients who were exactly alike, 50 would develop in 3 years, 50 would develop after 6 years. But then how do you apply that generalized statistic to an individual sitting in front? These are the issues that I'm dealing with all. And that's where I need help with. I think what we can do, and we have so many normal samples, now that all the technology has developed, we can do these multi-omics. We can use AI to really handle all this large data sets, petabytes of data that would come out of it, and come up with simple signatures that can tell us from day one what is shed into the blood, what proteins, what metabolites, what RNA and DNA pieces are being shed into the blood, the collection of which could tell us what the behavior of this disease is going to be in this individual versus another one. I think that it's so obvious to me that this is what should be done. I have all the samples needed for it. So all the heavy lifting has been done. What we need is some resources to do this. Now, that's about liquid tumors, and I'm working on all of that. So, for example, I go back for one step and just show you that the company Regeneron, that was part of my oncology think tank, has performed whole genome sequencing on my entire tissue repository. And that is a huge amount of data that's sitting in the cloud now, and we are analyzing. We are now next going to do transcriptomics and proteomics. And with the company Grail, which has a presence in the UK as well, we are looking at the entire tissue repository through these methylation profiles that they have had. Their platform for methylation is very dramatic because they have the machine learning has revealed something very interesting, that from a very small piece of DNA that's just floating because it has been released by a dying cancer cell, a tiny piece of DNA. This, after being trained on billions of pieces of DNA, trillions of pieces of DNA, their AI platform can tell us if this little piece of DNA, which doesn't have any mutations, by the way, just based on the methylation of pattern of genes in it, can tell us if it's coming from a cancer cell or a normal cell. It's an unbelievable advance just from the methylome. Such a simple thing. So it's not like I'm sitting not doing anything. I am harassing everybody to work with me and gotten Regeneron to do the genomics, gotten Grail to do the methylome. And now we are progressing with proteomics and transcriptomics. And once all the multi-omics are available, then I'm very confident that we'll be able to get there. But what about solid tumors, which are the real problem? Because they are the majority of cases. Well, we need to look for high-risk patients in solid cancers, and one such category is cancer survivors. Meaning, if you have one cancer, you are at risk of not just recurrence of that cancer, you are at risk of developing an entirely new cancer. So 1 in 5, 20%, that's a huge number. New cancers appear in someone who has survived one cancer. So take example of my husband. He at 34 had a solid cancer diagnosis. He survived it. At 57, he developed a leukemia and dies in the prime of his life. So a solid tumor and then develops a liquid tumor at 34 and 57. And this is the problem, that whatever was causing the stress so that the first cell appeared is still there when we cure the cancer. We don't take care of the underlying causes that cause the appearance of the first cell. And so I don't want anybody listening to me in the audience on Zoom to get anxious, because many of you or some of you may have had relatives who have cancer, friends who have cancer and survived, or maybe one or two of you have survived cancer. Now you will get anxious that, oh my God, I'm going to die of another cancer. No, the individual risk is only increased by 13%. But if you look at the actual diagnosed cases, then 20% have a history of another cancer. By the way, I have a patient right now I'm treating who has 5 active cancers at the same time. And I have multiple patients with 2 and 3 cancers. So somebody who has breast cancer and then develops pre-leukemia, myelodysplastic syndrome. And while they have these two, they go ahead, and these are new cancers. Renal, a node appears in the kidney. I'm saying it's probably breast cancer metastasizing. We take a look. No, it's another primary. So this happens a lot with MDS, especially, that I see other cancers appearing. So if there are 2 million new cancers diagnosed in the last year, then just do the math. 400,000 will occur in a cancer survivor. So cancer survivors are at high risk. And just like MDS is at high risk of developing leukemia or solid tumors, we can follow cancer survivors regularly because they are also connected to the centers. They come for follow-ups. So I created this coalition where I'm the principal investigator with Abdullah Ali. You met Dr. Ali in my lab. And I brought together Columbia Siddharth Mukherjee, who got the Pulitzer Prize for the Emperor of All Maladies. He and I share a lab, we work very closely. Sam Sia and Ken Shepard, whose work I just showed you. But we have an amazing group from Columbia, then Hopkins, Stanford, Harvard, Yale, Montefiore, Northwestern. I mean, the top institutions have all come together to make this coalition. And what we are trying to do now is exactly what I said. 20% of all cancers diagnosed are in cancer survivors. Of cancer survivors are diagnosed 5 or more years ago, and the relative risk, as I said, is only 13% higher. Currently, in 2019, there were 20 million cases nearly, and by 2040, there'll be 26 million cancer survivors. So it is a very good group to study. Cancer is the second leading cause of death in the United States right now. What we are collecting on these individuals are some of the samples that I have been collecting in my tissue repository for the leukemic cancers. So now we have all of this on cancer survivor, the tissue repository that I have started. And the idea is, I mean, I'm just giving you a timeline that, let's say, within 2 years, we have 50,000 samples collected, there will be 1,000 new cases. And now think, we have all the pre-cancer plasma, serum, saliva, biopsies, all kinds of things from before and then after they get cancer. Finding the canary in the coal mine, biomarkers, is very important. So it's not just that we are looking at those biomarkers I talked about. Abnormal cells can also be present. And that I have been thinking about for decades. What is the genesis of carcinogenesis? How does the first cell even begin? And I refuse to believe that this is a random DNA copying error by the polymerase, which makes a mistake just because of aging. It's too well orchestrated a response to think about that. So I feel that it's some stress that's causing cells to misbehave. And stress, not just mental stress, but stress within an organ, like in the liver, if there's an infection with hepatitis B virus, cells are dying right, left, and center. They're getting the signal fight or flight. Either develop a strategy to survive, you're going to die. And one strategy that cells develop to survive, I'll show you now, is very interesting. So I decided to produce stress in cells in my lab using all these different ways of producing stress. And what we saw was interesting. Here are cells happily growing away. And then when you produce stress, let's say by chemotherapy or starvation or hypoxia, you see the appearance of these giant cells. What are these giant cells? Well, we decided to follow one from the beginning, and we set our time-lapse video onto one and followed it, and nothing happens. This thing is out of my control. Nothing happened for 3 days, and then you suddenly see the cell is giving birth to little cells. Little cells are coming out, and now Jin Song Lu at MD Anderson calls it somatic cell pregnancy. So when I saw those giant cells, I said, my God, we should be able to isolate them by size. Literally using a coffee filter technology, pass the blood through a filter, and small cells will pass through, but the large cells will be trapped. And so I started working with Rare Cells Group under Professor Patrizia Paterlini, who had invented this machine with a filter. And this is ISET, stands for isolation by size of epithelial tumors. And she's was at the Pasteur Institute, a brilliant scientist, brilliant oncologist. And we started working together in 2015. So 9 years ago, I set up filtration devices in my lab and just started filtering the blood of the pre-leukemia patients, hoping to catch the first leukemia cell. But instead, what we started catching, so let's say I take 10 cc's of blood, I pass it through the ISET filter. We got the first leukemia cells. As you see, these are blasts, but we also got these giant cells, which look hugely pregnant. You can see how many nuclei are in this polyploidal giant cancer cell. And now hundreds of patients that I've studied, in everyone you are finding these cells, and always with little cells literally coming out. So it seems that there is some mother cell there which gives birth to these cancer cells. Now these giant polynucleated cells have also been found in the blood of solid cancer patients. I'll show you data on 5,000 such cases. Look at these giant cells. This is the size of a normal white blood cell. Compare that size to these cells which are also in the blood. So somebody has pancreatic cancer, someone has ovarian cancer, but you're finding these giant cells circulating in the blood. These are not tumor cells. These are not CTCs. So they were called initially cancer-associated macrophage-like cells because they had macrophage markers. And it seems that size matters. So let's say you have a cancer patient, and this patient has a colon cancer. You see right here is the colon cancer. But you are taking liquid biopsy. You are taking blood on this patient, passing it through a filter and finding these giant cells. Well, if the size of that giant cell is like 0 to 49 microns. You don't have a laser pointer. This thing is impossible. So you see, if the size of this giant cells you find in the blood is 0 to 49, then actually the prognosis is quite good. Good survival, isolated tumor. But if the size is 50 to 99 micron, there's already a metastatic lesion in the liver. And the survival is now coming down. But if the size is more than 100 microns of these giant cells, then survival is horrible. There are lesions in the brain, in the lungs, in the liver. It's metastatic disease all over the place. So just the size of these cells even matters. Now, the most unique feature of these cells is that they are hybrid in nature. What does that mean, hybrid in nature? In liquid cancers, polyploid giant cancer cells may arise from the fusion of a parenchymal mature macrophage with a stromal cell. And in solid cancers, fusion of the same macrophage with an epithelial cell. And so, most accurate name for these polyploid giant cancer cells is really cancer hybrid cells. And this is my origin story. That a tissue cell, let's call it a liver cell or a pancreatic cell, is under stress for some reason because there's an infection in the organ, exposure to toxins, or an inflammatory response. Aging is the worst carcinogen. Uh, Cancer is a disease associated with aging. Why? Because with aging, there is chronic inflammatory responses that start in different organs. And those are the inflammatory responses that put cells under stress. And if this tissue cell is under severe stress, it can make mistakes in its copying the DNA under stress, but then it doesn't become cancerous yet. That thing only is conferring some form of immortality on it, but then it can fuse with a blood cell that had actually come to eat it up and remove it. Instead of being removed by the macrophage, it fuses its genome with it and now becomes not only immortal but mobile. And that is a question that has always fascinated me, that in the body we have certain rules. If a cell is born in the liver, it stays in the liver. Born in the brain, it stays in the brain. Only in one disease, cancer, do cells walk out of their organs of origin. How do they become mobile? By hitching a ride on a blood cell. That's how they're becoming mobile. So basically, this hybrid cell then undergoes a very interesting phenomenon, which is that the nucleus keeps dividing, but the cell doesn't divide. But after it reaches a certain stage of 30, 40 nuclei, it will undergo depolyploidization. And now this is what gets diagnosed as cancer. And when we come in with treatment, this is what we end up killing. But that mother cell survives. And one of those other cells may survive. And now that surviving cell can fuse with a second macrophage. And as the nucleus starts dividing, in that next giant cell, each nuclear division can lead to more mutations being retained in the DNA. So that now there are so many more mutations at relapse and recurrence. And when this comes out, this is going to be a more aggressive and a more chemo-resistant disease. And this is what we see. Now, we have looked at, Abdullah performed this beautiful study at single cell RNA-seq and high throughput spatial analysis of in colon and breast cancer. Every case we looked at, these hybrid cells are present. We published this paper last year, and within a month, this paper came out in Nature showing the exact same thing for lung cancer using our exact technology, single cell RNA-seq, showing now in something like 900,000 single cell RNA-seq from 25 treatment naive patients with adenocarcinoma. Every patient has these same giant cells with markers of macrophage and tissue cell, the hybrid markers I'm talking about, which should not exist together on any normal cell. They either have blood marker or epithelial cell marker. For the two to exist on the same cell, that hybrid nature is unique to this cell. And then another paper comes out 2 months later showing brain cancer with the same cells, using again single cell RNAs. So I'm telling you that not just leukemia, myelodysplastic syndromes, and then colon and breast that we have looked at, every cancer that is looked at is showing the presence of this cell. So these cells can sometimes be detected years ahead of the appearance of cancer. And I just wanted to show a couple of cases. One is a heavy smoker but doesn't have cancer. And Professor Paterlini has reported this case. A liquid biopsy was done. They started finding giant cells, in fact, microemboli of giant cells. And then, where is the tumor? It took 3 years. Since 2009, they were detecting giant cells. In 2012, the CT scan showed a tumor in the lung, and this was resected, and the patient is cured since 2020. So here is another, this one is mine, an individual who's a perfectly healthy 66-year-old, non-smoker, nothing wrong with her, is giving her blood because every time we run a patient on the filter, we have to run a normal control. And in my clinic, I'm the one who's giving my blood every clinic day, 20 cc's of blood, because otherwise I'd have to take it from young medical students or residents who are in their 20s or 30s, and that's not a good control for 70-year-olds. I'm a good control for the patients, so they always bleed me. This woman was also giving her blood as a control, and lo and behold, we started finding these giant cells. It was very scary. I put her through multiple PET scans, CAT scans, MRIs, every biomarker possible. We couldn't find the tumor. But it was making me very anxious because the number of giant cells kept increasing with each passing year. 4 years later, we found the pap smear was abnormal, endocervical cancer appeared, and it was removed. And now it has been 3 years since her surgery, not one giant cell, and we do this every month. So it not only was a harbinger of cancer to begin with, it's also these cells have completely disappeared now after surgery. I told you that this device can detect the giant cells. Yeah, I just showed you that earlier because the signal would be large. Well, what you can also do then to detecting this device is if you detect that giant cell and there is an electrical field, you can communicate with that chip on this thing here and tell it to electrocute the cell next time it goes and just eliminate it right there. Because this kind of implantable device will have the ability to do that. And this is the exciting part. The Sentinel that we are working together on to develop this will not only, here's the electrical field, here is the cancer, the cell that is passing through the electrodes perform electrical impedance spectroscopy. But what you can do is on-demand killing of this cell. Also, you can detect all kinds of biomarkers, not just cells passing. You will be able to detect the biomarkers. And this is why it is so exciting and so important to work in a multidisciplinary approach. I'm the one with the giant cell story. They are the ones with the implantable device story. You guys are the one with the imaging story. We all need to work together to make this happen in the fastest way possible. The Sentinel will scan for cellular and molecular first cell stage cancer biomarkers using pairs of ring electrodes placed on opposing sides of the stent that can be placed at birth and continuously monitor until death. From womb to tomb, it will be monitored. Healthy individuals in the future. We hope that this is the kind of implantable device that in the future will be detecting all age-related chronic diseases. heart disease, lung disease, dementia, which is such a horrible problem. If these things are detected early at the first cell stage of the disease, then even lifestyle changes can make a difference. You can stop smoking, stop drinking, and start exercising. Ozempic might make a difference. Metformin could work, aspirin could work. Those are the things. Homeopathic treatment could work, I say. But at a certain stage, after that, things go out of control. I don't know why everybody is not looking at first in cell stages. Why is everybody so enamored by trying to find a magic bullet to cure cancer, despite having a century of experience that it doesn't work? The only cancers we cure are those we find early. And that has been my biggest problem. So, biomarkers for early detection, novel therapeutic targets, early intervention, arrest and reverse illness, compress morbidity period associated with aging, increase health span, and that is what will increase lifespan. So basically, I'm collecting serial samples on individuals, some of whom will develop cancer, and we can target the hybrid cells. Others, we are saving biomarkers on everybody, so plasma, serum, saliva, urine, feces, hair, nails on everybody is saved. But others will develop chronic diseases. Not every MDS patient dies of AML. Some will die of a heart attack. Some develop dementia. Well, we have their cells and we have their biomarkers also saved. And so with the biomarkers, the beauty is that if we perform multi-omics and actually find inflammatory markers, we can reduce inflammation, as I said, by simple things here. And that's, to me, a very logical algorithm, but unfortunately, I'm the only one who thinks so. Not many people. Oh, there's Siddhartha Mukherjee, me, our chair of medicine, some of the team, some of the individuals who work in one of my companies. Thank you so much for your attention. I'm going to stop. Happy to take any questions.
Thank you very much, Professor Raza, for that wonderful talk. I'll have some questions, but I'll give the audience and people online an opportunity to ask any questions. I see Sean has raised his hand. Sean?
So I would thank you for your talk. So I would ask about, you mentioned 20% of cancer survivors they develop chronic tumors. And you have also mentioned that these joint cells they develop under stress. These elements. So is it possible that these cancer survivors, because they are given chemotherapy, they are, because the cells, the other organs, they are under stress as well, they develop cancer because of that, or these mutation cancer cells. And also one question is that about this electrode, because it's killing those giant cells, but if for some reason it produces stress on normal cells as well, so why wouldn't it create those kind of cancer cells?
Yeah, both questions are very good. I worried about the first one, which is that is the treatment for the first cancer responsible for the second cancer? And that is not true to some extent. Why? Because many of these individuals just had surgery to remove their first cancers, did not have chemo or radiation therapy, and yet developed a completely unrelated second cancer. So surgery alone could not have caused that stress. But I say that people who did receive chemo, maybe they developed it faster, the second cancer. Instead of 10 years, they developed it in 4 or 5 years. So that's possible. The second question you're asking is, can the stent by itself cause the appearance of the first cell because of stress? It hasn't done in animals, but who knows? When we give it to humans, we'll figure it out. But nobody is going to start with healthy individuals. We're going to start with people who have terminal cancers, right? for whom the life expectancy is 3 to 6 months. If this is going to be deleterious to them, then we'll figure it out very.
Amazing.
Adam?
First of all, that was a fantastic talk. Thank you very much. And I'll be asking you to sign my okay. I've got two questions. So the first one, I suppose, is sort of linked to Sean's question. So these cells that we're actually communicating with these steps potentially, is the big naive computer science question, do they have any other function normally? Could they be doing something? Is there any chance of doing something useful that we might then be removing? And the second question, I know it's obviously not ready for this yet, but is it, I'm assuming this is going to be something that's going to be available for a lower cost so that it can be used globally.
Well, scaling up is very easy.
Yeah.
Yeah. You remember the human genome cost $15 billion for one genome. Now we do it for $200 in a couple of days. That took 15 years and billions of dollars. So that's easy to answer. And your first question is about, are the giant cells performing a useful function? Well, the answer to that is also important for you to know that any cell, any organ that's under chronic stress normally has tons of giant cells. So, for example, in the liver, in an adult liver, 20% of liver cells are fused cells, but it's a homotropic fusion between two cells of the same organ. This is a heterotropic fusion between a blood cell and a tissue cell. Cardiac muscle cells, 30% are fused giant cells. But then when we looked at the single cell RNA-seq data, we found giant cells with the hybrid markers in the normal adjacent area of the tube. And guess what? Because it's a single cell RNA-seq, you can look at the expression profile of the genes. So we looked at what is the transcriptomics? What is the transcriptome like in a hybrid cell that is present within the cancer, tumor's area itself, or this giant cell, hybrid cell, which is present in the normal area? And the transcriptomic profile is completely different. And we have reported all of this in the single cell RNA-seq paper. That yes, very rarely under stress, for example, somebody has the flu. Any infection could cause stresses, and under that stress, two cells would fuse, but they don't have somehow, they have a different transcriptomic profile than a hybrid cell from a malignant. We don't understand very much about it. But you know what, Adam? My job is not to keep trying to understand the mechanistic basis of this formation of the giant cell. I'm an oncologist. I am actually on the front lines and taking care of patients. So for me, anything that can help my patients takes precedence over trying to understand at an intellectual level what's going on. And so for me, as soon as I realized this, that there is something, you see, for all these years, everybody and their grandmother has been looking for a unique marker on a cancer cell, and we haven't found it. Well, this is what is making this giant cell unique, that you have two antigens that shouldn't exist on the same cell. So take that out. And so we proceeded immediately to start making a bispecific antibody to take those two out. I mean, take the cell out with the two markers. And so, yes, all those studies will come in with time as people become aware of these cells and start looking at them seriously. One of the problems is as soon as you put this kind of cell into an animal, they depolyploidization happens and you just have the regular cancer, but you don't have giant cells to study. So those are some of the issues that will have to be dealt with. They have to be studied by different technologies, like the way we are doing single cell RNA-seq, single cell proteomics, etc.
So just a follow-up question, if I may. How is this sentinel going to differentiate between large cells that create impedance, relatively high impedance, but they're not necessarily cancer cells or uh, you know, progenitors of cancer cells?
Yeah, that's why I showed that we can also measure biomarkers through, it's not sentinel, it's stentinel.
Stentinel, exactly.
It's a stent and a
Mhm.
sentinel. So even killing these rare normal giant cells which are circulating should not be causing huge problems. So let's say we kill some of them. So what?
Um, are they all stress induced, and are they all not doing anything useful? Coming back to Adam's point.
They're so rare that less than 1 or 2 in 50 billion, and not in everyone, in only 1% or 2%. So, I mean, I think they're negligible. But they are associated, giant cells are associated, or fused cells, with any stress. But fusion is homotropic, as I said. Heterotropic, very rare, it can happen, but it doesn't always lead to malignancy.
So you would be looking for differentiating between the two types of fusion before you kill them.
No, as I said, I'm just going to kill any cell that's expressing two markers and worry about whether I've done something later. Because the important thing is to clearly, in 99% of the cells, it's the malignancy. I'm interested in curing my patient. But you know, all these things, by the way, can work beautifully in animals. As soon as we take something to humans, all bets are off. Anything can happen. And so until we actually do these things in vivo, which I'm hoping to start the clinical trial now with the bispecific antibody, um, and then I either have to put up or shut up forever, because either it's going to, I'm going to start in advanced cancers, take out the giant cell. So the idea is treat the cancer first, use the antibody to take out the giant hybrid cell, and then see if you could prevent recurrence at least. And that would be a huge deal, because that would really help people with advanced stage cancers. Because you see, we can kill the cancer in these people, but then 6 months, 9 months later, it comes back. Well, it's coming back because that cell, the mother cell, had survived. If you take that out with the bispecific, will that actually matter? I don't know. We have to give it and see. Seems like a good lead, better than any other leads I've had.
So, quick question on bispecific antibodies. Have it tested in food
And in vivo, which you have to do in animals.
or cells that exhibit both macrophage and epithelial traits?
Yes, it's only taking the result.
One question I think what you're saying is these joint cells are the cause of, they themselves come from inflammation, right? So how do we prove that? For example, taking them out, all bets are off once you take them out and implant them in something else. How do you test that? That feel that this is the cause. One way we can do it as data scientists, for example. We have watched a single cell transcriptomic data. Has anyone tested whether it is able to predict presence of giant cells from anything other than the data of cells of these giant cells? So is it possible to predict the others, use information of the other cells that are found in the same sample and predict the presence of giant cells? And that means there is an association with these between.
We have looked at the normal surrounding areas and we haven't found anything. But I think your question is a good one, that this giant cell Is it the cause of cancer? I don't think so. Because to me, a cancer cell is a normal cell which is misbehaving. That's why we never find unique markers on them. So why are they suddenly misbehaving? And until now, it's been the somatic mutation theory of cancer, that it is because as we age, every cell keeps dividing and dividing, and then with each division, they pick up 2 to 3 random copying errors of DNA, and these mutations keep accumulating until we are 70 years of age, and then one of these cells just, is over the tipping point. That's the somatic mutation theory. I don't think that that applies in every, maybe in some cancers, but to me, it has always been that it's not a genetic issue, but it's a cellular issue. The whole cell misbehaves. Why? Because there's something in the surrounding of this cell that's forcing it to develop some strategy or do something crazy. So the real cause of cancer, if you want to think about it, goes before the first cell. It is that's what I call the first cell stage of cancer. That a stage is first set up for this cell to appear. And what is that first cell stage? We propose to use blood as a window into looking at all of this. Pick up all the biomarkers you can from the blood. Study the hell out of it. Do all the multiomics, any test you can on the blood of individuals before they develop cancer, after they develop cancer, and look at what stress markers are you picking up. And then can you neutralize those stress markers? Were they the cause? But then those stress markers came from some infection, something else. So then what was that cause? So in the end, if let's say hepatitis B virus is so commonly associated with a hepatocellular cancer, is the virus responsible for it, or the inflammation it set up, or the cells that arose from that inflammation, or the cells that were born out of that giant cell? What is the cause of cancer here? It is a process. It is a whole long evolutionary thing. In my book, The First Cell, if you guys have read it, I have talked so much about this clonal evolution, but then evolution of all these microenvironmental changes. I call it the mist of aging. Um, MIST means M, it's an acronym. M stands for mutations which are accumulating in a cell. I stands for your immunologic responses to clearing out damaged cells are decrepit. They're not that efficient anymore. S stands for senescence, collection of senescent cells which start hanging around organs with age. A cell that doesn't die but stops doing any useful function is in a senescent stage, but it's producing all the horrible toxic garbage that needs to be cleared up. But in an aging body, that's not happening. So the whole environment is getting poisoned. And the T stands for actual there appears actual spacing between the cells. So there is tissue spacing changes because, for example, in a healthy 21-year-old person, if you look at the bone marrow, 70% of the cells in the marrow will be hematopoietic cells, and 30% will be these large fat cells. But if you look at a 70-year-old's marrow, then it's reversed. 70% are fat cells and 30% are the hematopoietic cells. So fat cells are just there occupying space. Now it's causing a serious disturbance in the physiologic gradation of signaling from one cell to another, just because of the presence of these. So there are so many changes that are simultaneously occurring in an aging body that then produce these toxic, stressful conditions. That it's also called the tissue field theory, the TOFT of cancer. So there's somatic mutation theory, the TOFT theory that takes into account. I'm saying that it's a reductive approach still to keep looking for that one cause. It's kind of a reductionist approach. I prefer a more pluralistic vision. I mean, think in a holistic term of what is exactly happening all around. I mean, disease is not just manifestation of one particular thing which one magic bullet will fix. Sorry to be giving such long-winded answers, but this is what I have spent my whole life thinking about, and it's hard for me to say it in erudite little phrases. Sorry about that.
Yes, yes.
Just thank you. Amazing. I think the idea is fantastic. Please don't get me put in the toilet. You just explained what it is. How you apply these reductions. Some people, like me, they argue that, well, you keep your giant cell line might be the most reductions approach. The way you put it, you want to use it as the most magic bullet, as I can name it, because you not only can use it for cancer, but like all other diseases too. So to me, it also sounds like setting the magic bullet. Nevertheless, I do understand mechanisms that you have explained, and I do understand the potential. To be honest, I think even if it can only work for blood cancers, it's more than amazing, which I can assume based on the well, things that you just explained, it definitely works there. You have evidence for that, which is amazing. Perhaps one of the reasons of my skepticism is I cannot get my head around how this can be used in study. You have explained how this works. But maybe something that can help is that have you tried looking for giant cells in normal cases like people who don't have any cancer, like but a big population? You see how many show giant cells. If we can say, oh, this is really my marker of something that's
I love your comment, Mustafa, because it's exactly what I worry about. To have such fixed notions that, oh, this giant cell is the cause, or that's religion. That is not science. Science is skepticism. Every step of the way, we have to remain skeptical of what we are saying. And this is why I worry constantly about what if this cell doesn't matter? What if it's the first cell stage that matters? What is causing the cell to appear? I mean, so don't think that I'm tied to the idea of this magic bullet is going to take this out and fix everything. No, I'm so worried and so concerned about all of this. The one thing I will stick to as a doctrine or as a dogma is everything will be curable and preventable or helped by finding it early rather than late. That is my one thing that I'm not going to retract. Everything else is retractable. Yes, I'll take out the giant cell and I admit it to you. I don't know what it will do once I give it to humans. Maybe it will do nothing. And then, as I said, I'll put up or shut up. But no, I'm already making place for myself by saying, no, we have to look at all the multi-omics biomarkers that are also being shed. Maybe we'll find something to correct there, or maybe we have to do the two together. I don't know that yet. And to answer your actual question, which was, have I studied lots of normal people? Yes, with every sample, we run a normal sample. That's what I was telling you. For example, I feel like I'm tested for the giant cell every week, which is good. And if it appears, I'm panicked, but then, oh, I had a cold kind of thing. But we don't find it.
it's really good.
In the interest of time, see if there's anyone online who's got any questions. We've got about 15 more minutes for our own group discussion, but let's see if there's anyone online who may have any questions. Don't see any questions online. In which case, should we close the Zoom and carry on with our group discussion? What should we do?
Yeah,
Yeah.
that would be good.
Okay, well, thanks very much again.
Thank you.
Everyone online? Adam, you want to make any announcement for next week or next seminar?
Yeah. Right, thank you very much, everyone in person and everyone online for joining our seminar. So a reminder, our next TIA Centre seminar will be next week. It'll be on Monday. And we'll be joined online by Tong Ding from Harvard Med School, and this is going to be on the new foundation model, Titan.